Parallel programming enhances computational efficiency by enabling simultaneous data processing. GPU-GPU communication is crucial for high-performance computing, allowing multiple GPUs to work together seamlessly. Techniques like peer-to-peer memory access and communication collectives, such as RCCL and NCCL, optimize data transfer and synchronization, significantly boosting performance in complex computational tasks. GPU-GPU communication enhances high-performance computing by utilizing peer-to-peer memory access and communication collectives like RCCL and NCCL. These technologies enable efficient data transfer and synchronization between GPUs, crucial for tasks such as deep neural network training. Understanding APIs and programming examples, like remote vector addition, is essential for optimizing performance in parallel computing environments. GPU-GPU communication leverages peer-to-peer P2P memory access, enabling direct data transfer between GPUs. Key APIs facilitate this process, exemplified by a remote vector addition. Communication collectives, like RCCL/NCCL, enhance performance through collective operations, crucial for tasks like deep neural network training. Understanding these mechanisms is vital for optimizing high-performance computing and machine learning applications. In high-performance computing and machine learning, multiple GPUs collaborate to handle large datasets or complex models. Efficient data transfer and operation synchronization between GPUs are crucial for scalable performance. Specialized mechanisms and libraries enable faster data exchange and coordinated computations, addressing these challenges effectively. Peer-to-peer memory access allows one graphics processing unit to directly access another graphics processing unit's memory, bypassing the host central processing unit. This reduces latency and increases bandwidth. On peripheral component interconnect express systems enable peer-to-peer by setting HSA force fine grain PCIe equals 1. Ensure graphics processing units support peer-to-peer and large base address register addressing for optimal performance. Key APIs for peer-to-peer memory access include HIP device can access peer, which checks if a graphics processing unit can access another's memory, returning 0 or 1. HIP device enable peer access enables this access explicitly from the host side. Once enabled, Graphics Processing Unit 1 can directly load data from Graphics Processing Unit 2's memory, enhancing data transfer efficiency. The VEC-add kernel performs standard vector addition, adding elements from arrays A and B into C. It operates on device memory pointers, abstracting memory location. The kernel code remains unchanged with peer-to-peer memory access, ensuring seamless integration and efficient computation across GPUs. Two GPUs are identified: Memory GPU, ID 1, and Calculation GPU, ID 2. We check peer-to-peer support using HIP device can access peer. If access is unsupported, an error is printed and the program exits. Calculation GPU is set as the active device, and HIP device enable peer access is called to enable peer-to-peer access from Calculation GPU to Memory GPU. Set Memory GPU as the active device with HIP set device, Memory GPU. Allocate memory for DA, DB, and DC on Memory GPU using HIP malloc. Transfer host data, A.data and B.data to device memory DA and DB using HIP copy memcpy H to D. This prepares the data for processing on the Calculation GPU. The Calculation GPU is activated for kernel execution with HIP set device Calculation GPU. The VEC-add kernel runs on Calculation GPU, accessing data from Memory GPU via peer-to-peer. HIP device synchronize ensures completion before switching back to Memory GPU. Finally, results from DC are transferred to host memory using HIP mem PID to WOICHA. Ensure peer-to-peer communication support between devices, enabling it with API calls like HIP device enable peer access. The GPU kernel code remains unchanged, simplifying implementation. Host code must manage this feature, as peer-to-peer performance is unpredictable and requires understanding for optimal results. GPUs must support peer-to-peer access and large base address register address. Communication collectives are synchronized operations for data exchange among multiple processes in parallel computing. They enhance coordination in high-performance algorithms, crucial for simulations, climate modeling, and machine learning. Key patterns include broadcast, gather, scatter, all-to-all, reduce, all gather, and reduce scatter, each serving specific data distribution and aggregation needs. RCCL, the RCCL Communication Collectives Library, is tailored for high-performance collective communication in heterogeneous environments, optimizing data transfer among AMD GPUs. It offers flexibility by supporting CUDA environments. In contrast, NCCL, developed by NVIDIA, is the original library for efficient multi-GPU communication, specifically optimized for NVIDIA hardware, and RCCL originated as a fork of NCCL, initially mirroring its features. While NCCL boasts advanced capabilities like rail-optimized trees and LL128 protocol, RCCL has lagged in adopting these. Performance-wise, NCCL excels with superior integration into NVIDIA hardware, offering better scalability and robustness. RCCL, however, remains dependent on NVIDIA's ecosystem advancements. RCCL and NCCL support a variety of collective operations such as broadcast, reduce, and all reduce. They handle diverse data types, including integers and floats, ensuring versatility. Both are scalable, optimizing resource use from small clusters to supercomputers. They integrate with frameworks like TensorFlow and PyTorch, adapting to advanced microdevices ROCm and NVIDIA's CUDA architecture. Broadcast operations involve copying data from a single graphics processing unit to all others, using NCCL broadcast to distribute values from a root rank. All reduce operations reduce input data from all graphics processing units using operations like sum, with NCCL reduce, ensuring each graphics processing unit receives identical results. These operations are crucial for efficient parallel processing in distributed systems. Gradient aggregation is vital in deep neural network training. NVIDIA Collective Communications Library. All-reduce efficiently averages gradients across graphics processing units, ensuring model consistency. In distributed data parallel training, datasets are split among graphics processing units, each computing local gradients. This process is crucial for synchronized model updates, leveraging NVIDIA Collective Communications Library's capabilities for optimal performance. RCCL for AMD architecture features specific optimizations, enhancing memory bandwidth management and thread synchronization. Fully compatible with AMD's ROCm platform, it leverages diverse GPU capabilities. Benchmarking shows significant latency and bandwidth improvements. Key interconnects like PCIe, XGMI, InfiniBand, RoCE, and TCP/IP facilitate efficient intra- and internode communication. RCCL for CUDA architecture includes tailored optimizations like efficient kernel launches and streamlined data movement. It's fully compatible with NVIDIA's CUDA toolkit, ensuring seamless integration into existing applications. Benchmarking reveals significant improvements in execution speed and communication performance compared to standard libraries, enhancing overall efficiency in CUDA environments. RCCL significantly reduces latency by up to 50% in advanced microdevices and compute unified device architecture environments, enhancing collective operations. It boosts bandwidth utilization by up to 3 times through advanced algorithms and improves scalability by 40% within clusters. These optimizations lead to faster data exchanges and superior application performance. RCCL is pivotal in high-performance computing, optimizing communication for simulations and complex computations. In machine learning, it accelerates distributed training across GPUs, crucial for large data sets. For data analytics, RCCL enhances processing speed, reducing time to insight. In graphical rendering, it boosts performance by optimizing GPU communication for complex visualization. To program with RCCL, first create a communicator using NCCL Unique ID and NCCL COM-T. Use NCCL APIs like NCCL all reduce for collective operations. Synchronize operations with HipStream synchronize. Utilize group semantics with NCCL group start and NCCL group end to fuse multiple calls, enhancing performance and enabling concurrent progress. Initialize MPI with backticks MPI init for interprocess communication. Use MPI com rank and MPI com size to get the current rank and total ranks. Generate a unique ID with NCCL get unique ID NID on rank 0, then broadcast it using MPI bcast to synchronize all ranks. This ensures all communicators share the same ID for NCL comminute rank. HipSet device, my rank, assigns a GPU to each MPI rank. HipMalloc allocates sendBuff and receiveBuff on the device. HipStream create and SE sets up a HipStream for asynchronous tasks. NCL comminute rank, NCOM, NRanks, ID, my rank, initializes the RCCL communicator, synchronizing ranks, crucial for multi-threaded operation. NCCL reduce performs a collective operation, reducing data from sendBuff and storing results in recbuff. HipStream synchronize ensures completion. Post-operation, HipFree delocates buffers, NCCL com destroy com, releases communicator resources, and MPI finalize cleans up the message passing interface environment, ensuring a clean exit. NCCL reduce is a crucial API for collective operations. It reduces data from sendBuff and stores results in receiveBuff. Specify count for elements, data type like NCCL float 16, and op such as NCCL sum. Use com for communication and stream for execution. This ensures all ranks receive identical results efficiently. The all reduce operation involves two phases: reduce scatter and all gather. In reduce scatter, graphics processing units exchange and reduce data segments, like ABC on graphics processing unit 0, DEFE on graphics processing unit 1, and GHI on graphics processing unit 2, resulting in partial sums. All gather then distributes these partial results across all graphics processing units, ensuring each holds the complete reduced data set. Initially, each GPU sends a data chunk to the next: GPU 0 to GPU 1, GPU 1 to GPU 2, and GPU 2 to GPU 0. In subsequent steps, GPUs receive data, perform reductions, and pass results along. This cycle continues until each GPU holds a complete reduced segment. Finally, aggregated data blocks are circulated until all GPUs have the full dataset. The RCCL Tuner plugin API allows users to customize algorithm selection and protocols based on message size and system configuration, enhancing performance. The NCCL Net Plugin API enables the use of external plugins for diverse network types, ensuring flexibility and compatibility with different networking stacks, and supports in-network collective operations through optional call-net structures. RCCL's integration with MSCCL and MSCCL++ enhances GPU communication for collective operations. MSCCL uses XMLs for optimized sequences, while MSCCL++ offers efficient kernels for all reduce and all gather. On MI300X, NCCL min and channels boosts performance with fewer GPUs, and CPX and NPS 4 modes optimize compute and memory partitioning, achieving approximately 340 gigabytes per second in all reduce. RCCL faces setup complexity and limited debugging tools, with a performance gap due to its NVIDIA fork origins. Community resources aid in setup. Advanced Micro Devices plans a complete RCCL rewrite for independence, with 2024 enhancements boosting Advanced Micro Devices graphics processing unit data transfer by 30%. NVIDIA's NCCL advances include asynchronous GPU direct and deep network optimizations, enhancing cross-platform efficiency by 25%. GPU-GPU communication is crucial for scaling computational workloads. Peer-to-peer memory access reduces latency, enhancing efficiency. RCCL and NCCL libraries optimize multi-graphics processing unit operations, vital for distributed deep learning. While NCCL leads in performance, RCCL is evolving for advanced micro devices. Future advancements promise enhanced performance and compatibility, driving efficient high-performance computing and artificial intelligence applications. Thank you for your attention. We hope this presentation has deepened your understanding of GPU communication and its pivotal role in advancing computational efficiency and scalability.